My name is Nobuyuki Yoshikawa from Yokohama National University. Today I'd like to talk about energy-efficient superconductor digital circuit technology for high-performance computing. Because I'm developing superconducting digital circuits, the main purpose of my talk today is an introduction of a new energy-efficient logic called adiabatic quantum flux parametron. And I will show what challenge we have in this field, especially in terms of the logic design. They are my colleague and student in the Institute of Advanced Science in Yokohama National University. I thank all of them for contributing this study. This is the outline of today's my talk. After I show the motivation and background of this study, I will introduce the operation principle of the adiabatic quantum flux parameter AQFP logic, which is very energy efficient logic. Then I will talk about design methodology and the top-down design flow for AKFP logic circuits. After that, I will show the present status of AKFP logic development, including the demonstration of a RISC-type microprocessor. Finally, I will show what challenges we have in this research field. This graph shows the power consumption versus performance of the first-ranked supercomputer in the top 500 ranking. Now the world's fastest computer is Fugaku in Japan, whose peak performance is about 500 petaflops and power consumption is about 30 megawatt. It's really large. And if we extrapolate this line to the exascale computing performance, the power consumption reaches to the 100 megawatt. The cost of electric power is about $100 million, and we really need a low power logic circuit to reduce the running cost of the computation and also to save the Earth from the global warming. To reduce the energy consumption of logic circuits, we are developing the single flux quantum circuit by using superconducting material. The SFQ circuit utilizes the single flux quantum in a superconducting loop to represent the logical 1 and 0. The switching energy of this type of logic is given by phi 0 times IC, where phi 0 is the magnetic flux of the SFQ and IC is the bias current. Because the physical quantity of phi 0 is quite small, the switching energy is about 10 to the minus 19th joule at 4.2 Kelvin. This value is much smaller than the switching energy of CMOS circuit, which is given by charge Q times bias voltage VDD, and about 10 to the minus 16th joule. This is the main reason why we are developing SFQ circuits to reduce the power consumption of logic circuits. At present, two types of superconducting SFQ logic are mainly studied. One is energy-efficient rapid single-flux quantum logic, or ERSFQ, detail of which seems to be presented in a different talk in this session. This is DC-powered SFQ circuits, and its advantage is an extremely high clock rate, beyond 50 GHz. Its bit energy is relatively small and given by IB times phi 0, which has to be much higher than the thermal noise. Another one is the adiabatic quantum flux parametron, or AQFP, which is the main topics in this presentation. This is the AC-powered SFQ circuit. Its advantage is extremely low bit energy, thanks to the adiabatic switching of the intrinsically very fast superconducting devices. This is a comparison of bit energy versus gate delay of the several logic gates, where x-axis gate delay and y-axis is the bit energy of the logic gates. Between each gate is 100 micrometer length wires are connected. This green circle represents the data for high performance and low voltage CMOS devices. and these blue open circles are the data for AQFP. And these blue closed circles are the data for AQFP, taking account of the cooling power, where the 1,000 times of bit energy is added for the cooling power. One can see that the AQFP has more than 3 orders of magnitude better in terms of the bit energy compared to the state-of-art CMOS circuit. Okay, now let me tell you the operation principle of AQFP. AQFP is composed of a superconducting loop with two Josephson junctions, which is shunted by output inductance LQ. The excitation line is magnetically coupled to the superconducting loop to apply the excitation flux to the AQFP. The basic structure of the device was invented by Professor Goto of Tokyo University in 1984. In operation, the input current is applied from above at first. Then the AC excitation current is applied, by which left Josephson junction switched, and SFQ is entered to the left loop, resulting in a large downward output current. When the upward input current and the excitation current are applied, the right Josephson junction switches this time, resulting in large upward output current. This is the potential energy of the gate. And important thing is that the potential energy changes adiabatically during the switching event. Therefore, non-adiabatic energy consumption occurs during the switching event. This graph shows the calculated bit energy versus the rise time of excitation current. Y-axis represents the normalized bit energy, and the x-axis is the rise time of the excitation current. One can see that the bit energy of the AQFP is reduced proportionally to clock frequency in the adiabatic operation mode. The estimated bit energy is only 1 zepjoule, or 20 times of kBt, when the rise time is 1,000 picosecond. Next, let me tell you how the AQFP logic operates. As I mentioned previously, every AQFP has to be clocked by excitation current. Therefore, we currently use 4-phase clock to propagate the signals between the gates. The clock frequency is normally 5 to 10 GHz to use the benefit of the energy reduction due to the adiabatic switching. The latency of the gate is given by the clock period divided by the number of the phase, and currently 20 picosecond in 4-phase clocking. It can be reduced to about 5 picosecond when we increase the number of the phase. This slide shows the primitive of the AQFP logic. It is composed of buffer, NOT, and majority. Buffer is AQFP with an output transformer. NOT is cost-free because it can be made by a transformer with negative coupling. Majority made by connecting 3 buffers in parallel. So if 2 of 3 inputs are 1, its output becomes 1. And 2 of 3 inputs are 0, its output becomes 0. In our design methodology, the logic cell can be designed by placing 4 building blocks, that is buffer, NOT, constant, and branch, which is just a superconducting wire. Majority is composed of 3 buffers connected by 1 to 3 branch. By replacing the buffer with NOT and constant gates, we can make many kinds of logic gates. For example, NAND gate is obtained by using 2 NOT and 1 constant 1. For the fan-out, we need a splitter gate composed of a buffer and branches. Currently, 1 to 4 splitter is available. The physical layout of AQFP basic cell is shown here. To implement AQFP circuits, we are using a 4-metal layer Nobuyuki Josephson process provided by AIST in Japan. This is an example of layouts of basic cell, buffer, node, and constant, whose size is 30 micrometer by 40 micrometer, using the process with the minimum feature size of 1 micrometer. We can see that the symmetric design in the layout to reduce the parasitic coupling between the excitation and output inductance. We are also developing the AQFP cell library for MIT 8 metal layer process, where the cell size is reduced to 15 micrometer by 20 micrometer. By using the basic gate, AQFP logic circuits are designed similar to the CMOS standard cell layout approach. At first, logic gates are placed horizontally. Then the gate-to-gate wiring are made, and the wire to apply the excitation current are connected. Finally, the symbols are replaced with the physical layout. In order to make large-scale AQFP circuits, we are developing a top-down design flow. Here we will start with the Verilog behavior description and doing a logic synthesis to obtain schematic view. Then we will do the simulation to check the function and timing, and we will get a layout view. After performing the layout check, the data taped out and the chip will be fabricated. As for the logic synthesis, we are using a YOSYS to get an or not-based netlist from the behavior level description. These netlists are mapped to the AQFP logic using the AQFP cell library. Due to the special features of the AQFP logic, we are doing several post-synthesis. At first, we have to insert the buffer gate to equalize the phase number of each logic level, because the AQFP is clocked by a 4-phase clock. We also have to insert the splitter gate for fan-out. The number of NOT gates can be reduced by embedding NOT gate into the input of the logic gates. As for the placement and routing, we developed placement and routing tools by using the genetic algorithm and channel routing algorithm. One important feature of the AQFP circuit is that there is a wire length limitation between gates, because signal current amplitude is reduced with the increase of the wire length. At present, we set a soft wire length limitation, where the maximum wire length is 1 millimeter. This is a result of the GA optimization in the gate placement. You can see that the substantial reduction of the logic level is obtained by using GA. We designed several AQFP circuits by using the developed automated top-down design flow. AQFP logic circuits, including 4-bit shifter, 12-bit instruction decoder, 16-bit carry look-ahead adder, and the 8-bit shifter were designed up to date. At present, 90% operation of the 16-bit carry look-ahead adder is verified by measurement, and its full operation is under investigation. We are developing AQFP RISC microprocessor named Mana Lineup, and this is the latest result, which are presented in Symposia on VSI technology and circuits of this year. This is a block diagram of AQFP 4-bit RISC microprocessor. The estimated energy consumption is 15 femtojoule per operation at 5 GHz operation, including the cooling cost. It was implemented by using the aced Josephson process on 1 cm die, and its total junction number is about 2000. In the experiment at low speed, all operations, including ALU operation, register file access, branch, and store operations were confirmed with acceptable AC bias margins. We have several challenges in logic design right now. The first thing is the logic synthesis taking account of the path balance. In present circuit design, we have to insert a large number of buffer gates to make a path balance. For example, about 80% of Josephson junctions were used for the path balance. So we really need to reduce this number. The second is the majority-based logic synthesis. Because we are generating an or not-based netlist, then mapping them to the AQFP gates right now. So direct logic synthesis using the majority gate is attractive to reduce the number of the logic gates. The third is the design methodology for the clock trees. Because every logic gate needs an AC clock with multiple phases, efficient clock distribution with low clock skew is essential. So far, I introduced the AQFP circuits, and here I'd like to talk about our next target to achieve further reduction of the bit energy of logic circuit, that is reversible QFP or RQFP. AQFP buffer is basically reversible logic, so there is no minimum bound in the bit energy. But majority has 3 inputs and 1 output, so the entropy of the information is not conserved during the switching. The minimum bit energy is limited by KBT-ln2, known as the Landauer limit. By using an AQFP gate, we can make reversible majority gate, whose schematic is shown here. It has 3 inputs and 3 outputs, and entropy is conserved during the switching event. This is calculated bit energy of 1 bit per adder using AQFP and RQFP, taking account of the thermal noises. One can see that the bit energy lower than KBT-ln2 is obtained in the RQFP full adder. One problem in the RQFP is the increase in garbage bit numbers, which affects the number of the gate and hence the total energy consumption. Effective logic synthesis is highly demanded to reduce the garbage. This is a summary of today's talk. It was shown that the AQFP is extremely energy efficient logic. Design flow is similar to that of CMOS, but there is some difference, like majority-based logic, multi-phase AC clocking, and wire length limitation. Several challenges were pointed out as shown here. Thank you for your attention.